much for attending. We're going to talk about salt domes in the Houston Beaumont area. I have some new ideas. These are old domes, but I think seismic technology could really revitalize them. So here I have a little picture myself here. Charles and I have spent some time visiting the surface locations of salt domes just south of Houston. And here's a well on West Columbia. So I hope you'll find this interesting. We're going to talk a little bit about the history of some of the bigger salt domes. We're going to show a salt dome that isn't very productive and talk about that. And I have some examples of salt imaging through time that if you haven't been in the industry as long as I have, you'll be surprised of what that looks like. So here's an overview of my talk. Salt dome production in the Houston area really catapulted Texas into fame as a leading oil producer from approximately 1920 to the 1960s. But in the 1980s, approximately, the oil industry just wholesale left and went offshore to the Gulf of Mexico to explore salt features there. And really only small independents are currently drilling these onshore salt domes, let's say in the Houston area. And there are several reasons they left, and my career was all part of this. One was that the salt domes seemed to have hit the end point of their production because the seismic was just really terrible over the domes. So it seemed like a bigger play to go offshore and spend the technology dollars you need to investigate the offshore, bigger reserves, better imaging, but it's like it was out of phase because they left the onshore, and yet 10 or 20 years later, seismic data vastly improved everywhere and due to new processing techniques. And it just missed going back to the onshore domes for them to have a new look. So my question is, do onshore salt domes have hidden, untapped reserves that have been overlooked by exploration? And I'll make my point that seismic processing is the key. So here's a map of the Houston area, where the greater Houston area is in this greenish color, and these red circles are piercement salt domes. So in my study, I looked at 33 piercement salt domes. Now there are some fields that are cored by salt, but I wanted to look at these salt stocks, so to speak. And if you may be familiar with some of the more famous ones, Humble Salt Dome, a Spindletop Salt Dome, Barber's Hill, and in the Houston area, there's a famous dome called Pierce Junction, and I live out here near Katy, where there's a dome called Hockley. So these names are in the literature. Our strat column, if you're not familiar with the Houston area, these salt domes are surrounded by Miocene, Frio, Yewa, Vicksburg, and Wilcox. And here are the trends. You know, this would be a Frio trend around the dome. This is a Miocene trend around the dome. And we don't see the Cretaceous in any of these wells. So here's the salt dome production in an Excel graph. And a Humble Dome is a big dome. It's not a giant field. It's about 188 million barrels. And so of the piercement domes, and the ones we're going to talk about, Humble, Spindletop, Barber's Hill are the three big ones. They're between 150 to 200 million barrels. Then we have Pierce Junction, and I want to call your attention to the steep drop-off. There's lots of domes, but as you get beyond, say, Pierce Junction, they're getting down to the 5 million barrel, the 10 million barrel, or even the 1 million barrel range. And so the question is, it's not just me posing this question, is why is it so abnormal on salt domes? Things may come to your mind. Maybe it's the size, maybe it's the faults. Well, let's just take a look at some of the elements. So here's the Houston Beaumont area, and even in the same trend, you have Humble with 168 million, and Barber's Hill, and then Hockley with 1 million, and San Felipe with 15 million. So they're in the same trend, they've got the same sand potential, same charge potential, but we have wildly different cumes to date. Now let's take a look at size. One thing that I really was surprised to learn, that the size of the dome has nothing to do with its productivity. For example, the giant bowling dome, which is 9,000 acres, is in the west side of town here, and it produces 33 million barrels. San Felipe is also a large dome, 15 million barrels, but the small but mighty Spindletop is only 700 acres, and it produced 131 million barrels. And here's Barber's Hill. These are all very similar size domes with a wide range of production. So I'm not the only one puzzled over this. Michael Halberty, in his famous book about salt domes, was puzzling over it. He had some theories, but it's obviously the interplay of several factors. So let's take a look at a really highly productive salt dome, Humboldt Salt Dome. It was discovered in 1903. It was a major oil producer. It really put Houston on the map as a World War II oil powerhouse. Many companies were launched from the initial Humboldt Oil, Exxon, Gulf, Texaco, and many individuals created fortunes off the Humboldt Salt Dome. And it's in our art that people have, when you think about textbook salt, you really think about the Humboldt Dome. It is a very steep salt plug. And we know from well control that even down to 12,000 to 15,000 feet, it's still a stock. You know, it's not like necking off into like a thinner dome. And this is from the East Texas History website. I think this really depicts, if you could see it in geological, perfection, what the Humboldt Salt Dome looks like. Well, the Houston Geological Society has, of course, a dome on its logo, and I'm kind of convinced, since it was designed around 1949, that they are kind of thinking about the Humboldt Salt Dome when they made that logo. So here's a map of the Humboldt Salt Dome, and we'll take a look at this cross section here. And one thing you can see is it's got a rim syncline across the south end. And so having synclines on the north side and the south side is really a key to trapping hydrocarbons. It's also a prominent feature. It's tall. So if you subtract the syncline depth from the top salt depth, you get about 750 feet tall. It's got some good porous sands. But one thing, let's take a look at the cross section here. So this cross section goes from the northwest to the southeast. It's sort of diagrammatic, but you can see the dome beds, the beds thin onto the dome, from the Frio to the Vicksburg to the Yawa to the Wilcox. There's plenty of sand section, but the key, I think, is not only the rim synclines around Humboldt Dome, but the thinning onto the dome. So here you're starting to see the elements that make a dome quite productive. So I have a little view pack is a visualization product I have, and I loaded in all 2,500 wells in the Humboldt area, and I just wanted to kind of see, it looks like a pin cushion, and even though this would be like 65% chance of success, actually if you subtract out the cap rock wells, you virtually can't drill a dry hole on Humboldt Dome. It's that productive. So most of the sands that produce on the side are these like a coarsening upward Frio sand or a boxcar sand, and they're on water or they're filled to pay. They're like 50 feet thick. Again, another element of racking up the reserves. So I was just playing with my dome animations here. Let's move on to Spindletop, very famous dome. It's over east of us near Beaumont. And Spindletop was discovered in 1901 with the blowout on top of the hill. And again, like I said, it's not a very big dome, so that's why all these rigs are stacked close together. So I have it here, it's rising underneath. It's a pin cushion full of domes, and it was discovered by this guy, Patillo Higgins, in 1901. He was a self-taught explorer and a teacher, and one of the features, if you take a look at the top Frio map, is again, you have the syncline and a very steep drop-off south on the south side of Humboldt Dome. It's about 900 feet tall, so it's even taller than Humboldt Dome. But the synclines and the fact that it's such a prominent feature is very positive for trapping hydrocarbons. Now, Spindletop initially produced out of the cap rock, but that depleted. So in 1925, a very famous well that's been described by Michael Halberty went through the side of the salt and got into a pocket on the southwest side, and about half of the remaining reserves came out of that pocket. So here's the cap rock, here's the overhang, and now we're going to go and look at some seismic. We'll take a look at the overhang. So I want to make the point that overhangs are extremely rich, so you don't have to find oil all around the dome. If you can get under a salt overhang, you can stack quite a bit of reserves. For example, here's some wells here off of the overhang where they have stacked pays that are 100 to 50 to 100 feet thick. And in a small area, you're going to total up a lot of recoverable reserves. So again, this is in the lower Frio section. So here's my cross section across Spindletop. And here, depicting, the the wells are coming up to the salt near the overhang. Here's where they produce from the Miocene at the top. It was a blowout. And right away you'll see again the thinning beds on all the sections from the Miocene down to the Yewa. And the very productive overhang produces from the Frio and the lower Frio on the southwest side. So it's tall, it has thinning beds, and it has an overhang. So let's go back in time. This is 1970s unmigrated seismic data. And this is a publicly available data line because you can go to this museum called the Gladys City Boomtown Museum over in Beaumont, and it's on the wall. And everyone just stares at it. It's so terrible. I mean, there's a salt dome in here somewhere, and these arcs, if you're familiar with seismic processing, are because it's unmigrated. So somewhere inside of here is a salt dome, and you can see the frustration they must have been when they tried to use seismic technology to drill development wells. So this is a 3D from the 2000 era. It's pre-stack time Kirchhoff migration, and there's been great improvement in identifying the top of salt here, but we still have a lot of incoherent reflectors on the sides. And here, now for the first time, we see this little thumb sticking out, and this is the seismic imaging of the famous overhang, and these are the beds in the Frio that come up to make that very productive pocket. So I did a little sketch map on top of it, and you really have good quality sands all around the dome, but see the extreme thinning as you come up onto the pocket. So this is be a great exercise to backstrip this and figure out, obviously the salt movement is not only filling the pocket, but it's dragging up the beds underneath it. The Frio of Vicksburg tends to be kind of shaly, as we saw in the last cross-section, so most wells only go to about 6,000 feet on Humble Dome. And I put in my interpretation, I think the dome is probably leaning into its overhang, but actually the seismic data really doesn't confirm that. So how do we really know what any salt dome looks like? I mean, are there hidden traps? These older pre-stack time data, we've already been shown that it has a lot of limitations. So how do we really even ever know what a salt dome looks like? Well, I've been looking through the literature and now finding some of these images from the wave equation migration, and this is from Interpretation magazine. And in this illustration, which isn't, in the Gulf of Mexico, you can see how clearly the reverse time migration and the wave equation migration image these salt overhangs to the point where if there was one that was undrilled, you would be able to image it by reprocessing that data. And this is an example from the Interpretation magazine of what a dome like Humble or a Spindletop might look like if you were able to reprocess it in great detail. So if we want to discover more oil pay, I think there's still opportunity onshore, but you would have to make the investment to process and shoot new data. So this is another productive dome called Barber's Hill, which is on the west side or the east side of Houston. And again, it has a very pronounced syncline blocking hydrocarbons from moving away to the north. So his cross-section on Barber's Hill, again, now the overhang doesn't always have to be on the south side. In this case, the overhang is on the east side. And the productive pocket, which has really been described in the literature quite thoroughly, holds a tremendous amount of hydrocarbons. So it's a highly productive salt overhang stacked on the east side. This is another example where there isn't any deep drilling. So when you see this well goes to like 6,800 feet. I mean, that is pretty much all they've drilled, knowing that some of the surrounding domes were shaly. No one is aggressive about drilling the deeper section. So here we have a 1955 cross-section depicting the dome pocket, which looks like a little carve-out in this diagram. And when I just made a cross-section of my workstation, you can see literally hundreds of wells have been drilled through the salt into this pocket on the east side. So we'll have a cross-section there. And now we're going to take a look at, let's look at a salt dome that isn't very productive. The famous Hockley Salt Dome, which is near Katy on the west side of town. And Hockley Salt Dome is famous because you can go to a bird watching reserve right next to the dome, and as you stand on top of and look for birds, you can see the United Salt Mine, which has been operating since the 20s. They use the dome rock, to send salt to the east, and you can see a small hill. And actually the same man, Petit O'Higgins, visited Hockley, Humble, and Spindletop, and he saw the hills there before it was a populated area, and he marked them all down as potential, and they all are surface expressions of salt domes. But Hockley Salt Dome is not very productive, and the question is why? Well, one conclusion I came to is when you make cross sections through Hockley, there's no thinning going on in the beds. The beds are up tilted, but they're not thinning. And so this is again a big flag on Hockley Dome. The only production they were able to establish is, well, they have a little bit of miocene on the northwest side, and this is on the southwest side. There are some wells clipped through the salt, but it's not a very big pocket. But I think the sands are somewhat discontinuous as well. It's almost like if you remove the dome, you would just have flat-lying beds through Hockley. And that is a troublesome thing to observe. So here's the Hockley Dome map. Hockley is not a very tall dome either. It is only about 350 feet from regional, so if you measure the syncline to the top, instead of getting 700 feet, you're getting 300 feet. And here's the small overhang. So I made a regional map around the Hockley Dome on the Frio, and this sort of is another big flag. It seems to leak to the northwest. So you have a leak point to this field here. You don't really have much of a syncline around Hockley Dome, and the giant Katy gas field, which is the TCF and the Wilcox, seems to that maybe it even has drained away some reserves because it's a physically taller feature in the subsurface compared to Hockley. Here's another poorly producing dome called San Felipe Dome. Has a little bit of a northern syncline, but again, not a lot of closure around it. So as we compare a productive dome called Barber's Hill to Hockley, they are essentially the same size, but one makes 135 million and one makes 1 million. The big difference is Hockley lacks the thinning, it has small trap closures. I think the regional thing indicates thinning, and Hockley, of course, because it's not very productive, doesn't really have stacked pays compared to all the stacked pays you see in Barber's Hill. So the conclusions here is that highly productive salt domes have salt overhangs, tall domes trap more oil, pay thickness, you have the ability in these domes to stack multiple pays. The formations absolutely must be observed to be thinning onto the dome, preferably all the way from the top to the bottom, so that it's continuously rising faster than the beds are being deposited. And even and better yet, it's being pulled up into like some kind of salt overhang. And I recommend always create regional maps. Many people sell prospects on all the domes, but all they make are local maps. And unless you make a regional map, you're really not seeing the dome in context. The less productive domes, the beds are parallel around the dome. Maybe they don't have synclines to the north to help keep the hydrocarbons from migrating out. And then you can pretty much identify them if you're doing a regional mapping project. So here's some references. If you're interested, I'd be happy to share it with people. And I don't know if I have any time left for questions.
You have plenty of time.
Mark Rowan, some company, I'm not sure what. Hi, Linda. So people have been looking deeper at some of the domes in Louisiana, at least, and looking beneath overhangs, for example. So I have a question for you, sort of approach. If you have a dome that has a lot of shallow production, is that better to go for because it's got a proven system, but maybe the risk is that all the hydrocarbons have gone shallow? Or do you go for ones where there's very little shallow production because it's all trapped deeper, or maybe it's not working? Do you have any thoughts on that?
Well, like I said, when the dome is productive shallow, most of the wells go to the productive horizon. So there hasn't been a lot of aggressive drilling to take a look at the deep section. So I think it's like a self-fulfilling prophecy. They don't go below the last great ones. The other thing that happens is that the operators tend to break up all the acreage around it, and they don't let anybody in to go to test deeper horizons. So my thoughts would be to go to the ones that aren't that productive shallow and just say, well, maybe we have, if we could image steeply dipping beds and faults underneath here, we can find something that, even though the shallow hasn't been that productive, either they didn't hit the right part, or maybe it's a deeper horizon, like maybe the Yewa or the Wilcox. So that would be my exploration opportunity. It's really difficult to go to a dome like Humboldt and be an independent and try to do a prospect there, because it's all solidly HBP from the historical operators and the current operators, and they're not perhaps that interested. I'd also prefer to go to domes that don't have an urban area on top of them, like Pierce Junction is covered by Houston, Sugar Land, and so you go to some of the domes that are out in the country, I think you'd have a little more opportunity to do some technology with the seismic and be a little more, have an exploration program, but you'd have to find a dome that you could not prove it had thinning in the deep sections from the well control that's already there.
Okay, thanks.
Yeah, my name's Robert Nail with TCEQ. And I've got a question for you with regards to the structure. I didn't see a whole lot of fault interpretation associated with a lot of your diagrams. Are you finding faulting associated with almost all of these domes?
Yeah, I've been working on the well control side, and I have from the literature, you know, like if we go back to Humboldt, if you go into the literature, some of the older geologists have put the faults in, but you know, I have not been able to personally work with the seismic data that you would need to map all the faults, but generally Humboldt is known as a classic shatter pattern on the top, and you know, so it has radiating faults that come out. I know there's some radiating faults on the Spindletop dome. So I would assume that that's another component that I wasn't able to bring in my talk, that faulting is very important to trapping on there. And if you find a dome that's maybe very small and it doesn't have any faulting, that would be a flag, I think, on, you know, productivity in the future. You know, the only way you get a big production is with a pocket in an overhang, which may have a fault associated with it, but just up against the dome is a very poor trap, because there's that potential for the hydrocarbons to just keep moving up dip. Is that kind of what you were thinking?
Yeah, that's good. Thank you.
I mean, I just want to bring in, there's a lot of interplay between all the trap elements that have a big impact on whether you're a 160 million barrel dome or a 10 million barrel dome. And I think this would be a great computer-aided project. If you could put enough information into something like AI and train it, it could go, because there are literally hundreds of salt domes in the Gulf Coast. You could have a team of people work them up individually, but if you got the criteria down and they were able to use the seismic, maybe you could use machine learning to more rapidly give you ideas on which domes might have the deep potential.
Good morning, Vernon Moore. I was going to see if you had any more comments on what specific aspects of the thinning in the reservoir sections that you think was contributing to success.
Let's go to Barber's Hill. That's a pretty good cross section. I didn't have the time to put a lot of well logs into these things. I've just been looking at them with the well control. But so what exactly were you saying? I'm sorry, I lost my train of thought.
Yeah, I was just wondering what specifically about the thinning did you think was important?
Well, I think the thinning shows that the salt I believe the salt is moving into the overhang and it's pulling the beds up with it, and it's doing that almost as they're being deposited. So there's a gradual motion that, you know, the Miocene and the Frio are being deposited around the dome. The dome is at the same time moving into creating a pocket, and it's pulling the beds up so they depositionally thin. And all this creates like a good trap to keep oil and gas around the dome.
Okay, so more about the formation of the trap than, say, the reservoir.
Right. I mean, I've heard people say stuff like salt domes move later. Well, I don't see that. I think the salt dome is always a feature in all the domes. The question is its history of its movement. Is it inflating? Is it pulling into a pocket? I mean, domes don't just suddenly appear and cut through the section, you know, like maybe some people think like they penetrate the section. You always have a relic feature there. It could be very thin, but it's a differential compaction problem, and it's a salt movement because the salt is moving upward as the beds are being deposited. So you have to think of these things together. I think it would be wonderful to backstrip all this out. You know, things like David does in his research, and you learn even more.
Okay, thank you very much, Linda. Let's give her a round of applause.